boogie theorem prover that is going to construct the verification condition for us. And then the verification condition is actually checked by a constraint solver. So because we in Microsoft, we use Z3, it's one of the best theorem prover in the best constraint solver out there. It has won like many contests and stuff. So we use that one, it works pretty well. It was even really well. And either the property is verified or it's not verified. So in case it's not verified, we have a warning. And so in the compiler window, whenever we have finished to run the analyzer, we have a list of the warnings, and then we can review the warnings manually. So I wouldn't say this replaces code review entirely. This is more of a complement. Say, when we have millions of lines of code, say 10 million lines of code to analyze, we cannot afford, because we have very few, we cannot afford doing code review on 10 million lines of code. So we use this kind of tool to do the filtering, and then we focus on the locations where the static analysis wasn't able to prove that everything was safe. Any question about that? 5 minutes. Okay, I'm almost finished. So just to give a couple of numbers, on the first test case, the theorem prover was able to filter out 19% of the location of the assertions. So in 19% of the case, the assertions could be proven either, or could be proven true. So we don't need to review 98% of the cases. After a couple of more tests, actually, this number is nearer 90% than 98%, but still, it filters out a huge amount of the attacks you face. So that allows us to focus on the weak points, or the point that the prover was not able to verify. For 1 million, like order of magnitude, for 1 million line of code, we have about 100 warnings. So 100 warnings is something you can review like in 2-3 days. So 2-3 days of work for 1 million lines of code is pretty cost effective, right? And we've done just like this very simple case, like just adding one for this one simple property where you just need to add one assertion. This like requires the size different than 0 for xallocate pool API and for the related APIs. We uncovered multiple elevation of privilege in the Windows kernel. So it was about 10 bugs. And we found a couple of more by code review in other code bases, like code bases that where our tools don't apply yet. But the zero location pattern is definitely present, and not just in the Windows kernel. So look around you, like all those protocols where you have TLVs and stuff, where you receive from the network the size you're supposed to allocate. You know, I was mentioning mobile code area alone. Just look around. I don't have much time, so I'm probably just going to give a last example. If you're into Windows analysis, then you followed like the whole SMB saga last year. One of the bugs of SMB was actually a zero location. So it was a very complex case because it involved 3 different components of the kernel. So you had the server driver, so I can say it's SMB now. And then the server driver forwards request to other drivers, say the file system driver, passing through a component of the kernel called the IO manager. So sometimes you do a request that, imagine you do a request from the server driver to the IO manager using an API called IO do request with a tainted size, so the size is potentially 0. And then you pass the 0 value to the IO manager, and it performs 0 location, and then the pointer is passed to another driver. So each of those drivers is potentially like 1 million lines of code, right? So you don't want to analyze all of that. So what we do is that we put the preconditions, so the requires, or like the assert, if you prefer, we put them on the interface function between models. So with the domain-specific knowledge that we have, from the kernel modules or like from whatever component of the code base you want to analyze, basically we avoid to enter multiple components by just putting the assertions on the interface function, so we don't just have to analyze the top level components to find the bugs. Obviously, that would blow up if we have to analyze multiple millions of lines of code at once in multiple modules, then it's going to take forever, and you're not even sure that you're going to find the bug. So it's kind of practical just to put the assertions in the interface functions. Okay, I had a third part about DNS allocation, but I'm running out of time, so I'm just going to take questions now. And thank you for your attention.
Hi, thanks for the presentation. I have a question. Well, I really like you doing model checking and data flow analysis, all this stuff, but I don't really understand why why you shouldn't deal with the root cause. You know, why not just change the implementation of the heap and handle zero-size allocations like a special case instead of. Don't get me wrong, I really don't mind you guys patching bugs and stuff. I mean, that's a good thing probably, but why not just prevent people from, you know?
I understand. So, as I mentioned, actually, it's for compatibility with third-party code. So some people will actually do zero allocation on purpose, or you can have the pattern where you do malloc 0, and then you have a loop where you need to reallocate the buffer. So you do malloc 0 that is perfectly legitimate, and then you do realloc, 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 and then there is no bug, right? Because you should be allowed to do malloc 0, and then you do the reallocation of the buffer as the program gets executed, because you need more data, you need more space to put your input data. So if you just say, oh, a macro as a wrapper to malloc, if size equals 0, then return null, for example, then you're going to break lots of applications.
It's still perfectly possible. Of course, you have to change realloc as well, right? And instead of returning null, you have to return 1, 2, 3, 4, for example, and then check that in realloc as well, and in free and all these.
I agree with you. Like fundamentally, you should not allow this kind of stuff. But it's a huge engineering effort. Like it's not just like 10 lines of code to change, right? You really need to change lots of code to do that, and not just in the allocator, but also the application that use the allocator. So there is a trade-off between like safety of the code and keeping it working as it is, right? So the code base is super huge. So you cannot just expect to do a simple modification and everything. You know, we have people who do mitigations really 100% of their time, and they have to build Windows, and they have to build Windows to run like thousands of checks. And sometimes the modifications are really simple. You wouldn't expect them to break anything, but the simplest modification can actually break the code in 10 different ways. So it's not trivial to just do a simple modification like that. We would like that. We discussed it. We discussed inclusion in the security development lifecycle for zero locations, but it's not there yet. So we might actually decide to put it in there, but currently we still rely on like code review and automated detection, or semi-automated detection for this kind of vulnerability.
How does your memory modeling work for the comparison?
I didn't get it, sorry.
A few slides back, you were showing how you did this analysis. Yeah, right there. Memory model, what are you doing with that?
So as I mentioned, the memory model actually is a set of axioms that describe how memory access works. So you'd say, for example, you'd say whenever you write into a variable, you'd expect that next time you read it, you'll have the value that you wrote, right? This would be an axiom described by the memory model.
So you're saying this thing in memory has to follow these rules, etc.
Exactly.
Okay.
So depending on the architecture, the axioms of the memory model are different. For example, on ARM, you might have to write twice the same value in a variable to make sure that next time you read it, you actually read the same value. So that's weird, but like this is how it works.
I was just wondering if you have all this architecture already, Why only use it for zero malloc detection? I mean, you could use this for all sorts of weird things, like execution of code that shouldn't be executed, or buffer overflows. A number of things.
As I mentioned, the buffer overflow problem is very complex. So you can have a generic buffer overflow finder, but it's going to be really noisy. It's going to give you lots of false positives. So the idea of this talk is to have this very simple property that we know is difficult to handle for developers. So we limit ourselves to this particular pattern, and we uncover those bugs. So you could do the same, say, for particular size, say FFFF, say, because it's a boundary value, so boundary values are harder to handle for developers. But there is no such, actually, if you look at the literature, you'll see that lots of people have attempted automated buffer overflow detection, and lots of people do that, but most of the time it's super noisy. So you have hundreds, if not thousands, of false positives. So that's why you have to reduce the actual analysis you do in order to be able to review the warnings in a reasonable amount of time.
I'm not going to take the time, but I don't agree with you, because if this is a theorem prover, then that proves that there is no buffer overflow, or it proves that it is possible. So there is no false positive, and that's it. So the other possibility is that the way you transformed your code into the prover is noisy, and therefore the prover will give you a noisy output, but the prover is mathematically gives you a proof.
Okay,
but the question is, do you have the firepower, so the amount of clusters and CPUs to actually crunch through all that code, which I develop set solvers, so I know how difficult they are in terms of speed. So yeah, I understand, but I don't agree with you. In theory, in practice, of course, it's impossible because it's just too much time. But it would actually give you an answer: it's true or false, and that's it. It won't give you any noise at all.
So in theory, you can also put Paris in bottle, but we ain't with practice, right? So we want to do things that work. So indeed, in theory, theorem prover would be no noise at all. You can actually do. No, well, we can talk about it later, but in practice, you really have to reduce your analysis to what's actually tractable to review. You cannot. We don't have so much manpower on that. I mean, one of the disadvantages of theorem proving is that you need an expert to review the result, right? You cannot expect anyone to review the result of a theorem prover. So finding people that are able to review the result of a theorem prover is not so straightforward. So when you have millions of lines, dozens of millions of lines of code, you cannot expect to just fire a theorem prover on them and then find all the bugs, then you finish, your product is perfectly secure. The reality doesn't work like that. So we can talk later.
Why don't you do cleaner programming? So, for example, if you have some systems that have to work, maybe some embedded systems that control airplanes or stuff like that, then you would make some range checking, or even make a malloc with an assert. That so if you start to make a malloc with zero size, it will assert, and then you get a trace record, and then you can trace it if you debug it, and you see, oh, the trace that it broke at address number so and so, and then you go to trace memory, and then you see that there was a zero size malloc, and then you find what was the condition, and then you have to find that somebody was too stupid to make the code in the right manner. And so it would be better to fill such evil places with asserts that generates errors, and then you can trace this.
So if I understand correctly, this is a dynamic approach to detection, right?
Yes, and on runtime. So every time you write software, you have to test it in the system, and you get test vectors, and then you have to run it some months, and then you will see if it behaves correctly or if it does make some problems.
Yeah, well, in theory, you should put all the checks, and then the code would be perfectly secure.
You also in practice. So if you make some software that doesn't only control a word processor, but maybe controls some evil machines, then you have to do this.
You should absolutely do this. Of course, you should like check the values of the API so that no zero allocation can happen.